Welcome to the Deep Dive, the show where we take complex stuff and really break it down for you. Today, we're diving into liquids and solids. Fascinating world, right?
Absolutely.
I mean, think about water. You've got solid ice you can skate on, liquid water you swim in, and then just invisible vapor in the air. Same stuff, H2O, but so different.
It really is.
Yeah.
And we often just accept it, but why? What's actually happening down at the molecular level?
Exactly. That's our mission today. We want to unpack the core ideas, the theories, the forces that make liquids and solids behave the way they do.
We'll dig into those invisible forces, look at their unique properties.
Yeah, like how a diamond gets so hard, or how those smart fluids work in cars. The ones that change how thick they are.
Right. The goal is that by the end, you won't just know what happens, but why it happens. Consider it a shortcut to getting your head around the chemistry that literally holds our world together.
Okay, let's jump in. So, gases. We kind of picture particles zooming around, far apart, lots of energy. How do liquids and solids compare? Where do they fit in?
Well, gases, like you said, low density, easy to compress. The molecules are pretty independent, weak intermolecular forces. Solids, completely the opposite.
Right? Dense, hard to squash, keep their shape.
Exactly. High density, very low compressibility, they're rigid. And that tells us the particles inside must be packed really close together, held by pretty strong forces.
Okay, so solids and gases are extremes. Where do liquids fall?
Liquids are this really interesting middle ground. And actually, they're often more similar to solids than gases.
Well.
Take water again.
Mm-hmm.
Melting ice takes about 6 kilojoules of energy per mole, amount.
Mm-hmm.
But boiling that same water takes almost 41 kilojoules per mole.
Wow, that's a huge difference. Nearly 7 times more energy to boil than to melt.
Precisely. And that's the key insight. It tells us that even in liquid water, those molecules are still holding onto each other quite strongly, much more strongly than in a gas, even if they're not locked into a rigid structure like ice.
So the molecules are still sticky in a liquid.
Very sticky, comparatively speaking. And you see it in density, too. Liquid water and ice have densities that are, in the same ballpark. Gaseous water, way, way less dense.
Ah, okay. So liquids and solids are both condensed states.
Exactly.
Yeah.
And the absolute crucial thing to grasp is that the difference between these states comes down to intermolecular forces, the forces between the molecules.
Not the forces inside the molecules.
Correct. A water molecule is always H2O, whether it's ice, liquid, or steam. The HO bonds within the molecule aren't breaking when you boil water. It's the forces holding different H2O molecules together that are being overcome.
Got it. Okay, these intermolecular forces, you said they're the key. So what are they exactly? How do they work? Give us an example. How do these weaker between-molecule forces cause something like water's high boiling point?
Right, good question. Even though they're generally weaker than, say, a covalent bond inside a molecule, they absolutely dictate the state of matter. So first up, dipole forces. These happen between polar molecules. Molecules that have a permanent separation of charge, like a tiny little positive end and a negative end. Uneven electron sharing does that.
Like tiny magnets.
Exactly like tiny magnets. The positive end of one molecule attracts the negative end of its neighbor. In a liquid or solid, they try to line up to maximize this attraction.
Makes sense.
Now, a really important, strong type of dipole force is hydrogen bonding.
Ah, yes, I've heard of that one. Crucial for biology, right?
Absolutely crucial. It happens when hydrogen is bonded directly to a very electronegative atom, specifically nitrogen, oxygen, or fluorine, NO or F.
Why those three?
2 reasons. 1, the bond becomes extremely polar, so the hydrogen end is very positive. 2, hydrogen is tiny, so it can get really close to the lone pair electrons on the NO or F of a neighboring molecule.
Okay, so superpolar bond, tiny atom, gets up close.
And that close approach makes the attraction much stronger than a typical dipole force. And that is why water's boiling point is so incredibly high for its size. You have to pump in a lot of energy to break those numerous strong hydrogen bonds just to get it into the gas phase. Same for ammonia, NH3, or hydrogen fluoride, HF.
Okay, that explains water. But what about molecules that aren't polar, like methane or oxygen gas? They don't have permanent positive and negative ends. How do they stick together at all, even to become liquids or solids at low temperatures?
Great question. That's where London dispersion forces, or LDFs, come in. Sometimes just called dispersion forces.
London forces. Sounds intriguing.
It is. Even in a nonpolar molecule or just a single atom like argon, the electrons are constantly moving, right? They're whizzing around the nucleus.
Yeah.
So just by chance, at any given instant, the electrons might be distributed unevenly. more on one side than the other for a fraction of a second.
So it gets a temporary lopsided charge, a fleeting dipole.
Exactly. An instantaneous dipole. And this temporary dipole can then induce a similar temporary dipole in a neighboring atom or molecule. Sort of pushes its electrons away or pulls them closer for a moment.
Okay, like a ripple effect.
Very short-lived one, yes.
Yeah.
This creates a weak temporary attraction. Now, the key thing is how easily the electron cloud can be distorted or squished. We call that polarizability.
Polarizability. Makes sense.
Larger atoms or molecules, the ones with more electrons spread over a bigger volume, are generally more polarizable. Their electron clouds are easier to distort.
So they have stronger London dispersion forces.
Correct, which is why if you look at the noble gases, the freezing point goes up as you go down the group. Xenon, with lots of electrons, has stronger LDFs and freezes at a much higher temperature than tiny helium.
Interesting. So even though they're weak forces, they add up, especially for big molecules.
They can add up significantly. Here's the real kicker. For very large molecules, the total effect of all these little London dispersion forces can actually be stronger than the dipole forces in smaller polar molecules.
No way. Really?
Absolutely. Think about large nonpolar molecules like those in lubricating oils or waxes. They can be quite viscous liquids or even solids at room temperature, held together purely by LDFs. Meanwhile, a smaller polar molecule might be a gas. So never underestimate LDFs.
Okay, point taken. So with these forces in mind, let's clarify. Physical versus chemical change. Boiling water.
Physical change. You're overcoming intermolecular forces, the hydrogen bonds, but the H2O molecules stay intact.
Burning methane.
Chemical change. You're breaking CH bonds, OO bonds, forming new CO and HO bonds, completely different molecules afterwards.
What about dissolving salt, NaCl, in water? That seems fuzzy.
It is a bit fuzzy, definitely a gray area. On one hand, you still have Na plus and Cl ions just surrounded by water now, so it seems physical, but you had to break the very strong ionic bonds holding the salt crystal together.
And those are strong, like, covalent bonds.
Right. And you form new interactions, ion-dipole forces, between the ions and the polar water molecules. So because strong bonds are broken and new interactions formed, it has elements of a chemical change, too. It highlights that these categories aren't always perfectly neat.
Okay, that makes sense. So these forces dictate whether something is a liquid, but how do they affect how liquids behave? What properties emerge?
Good question. Several key properties. Let's start with surface tension.
Okay.
Imagine molecules inside the bulk of the liquid. They're being pulled equally in all directions by their neighbors, right?
Yeah, balanced forces.
But molecules right at the surface, they only have neighbors below and beside them. Nothing pulling them upwards.
So they get pulled inwards and sideways more strongly.
Exactly. This inward pull makes the surface molecules pack tighter and causes the liquid to resist increasing its surface area. It acts like a sort of elastic skin.
Which is why water forms droplets, trying to minimize that surface area.
Precisely. A sphere has the minimum surface area for a given volume. And liquids with strong intermolecular forces, like water with its hydrogen bonding, have high surface tension. You can even float a paperclip on water carefully.
Cool. What else?
Capillary action. That's when a liquid seems to climb up a narrow tube or is pushed down.
Like water in a thin glass tube.
Exactly. It depends on a balance between two types of forces. Cohesive forces, which are the intermolecular forces within the liquid itself.
Okay, molecules sticking to each other.
And adhesive forces, which are the attractions between the liquid molecules and the surface of the container.
Liquids stick into the tube.
Right. With water in glass, the adhesive forces are strong. Water molecules are attracted to the polar silicon dioxide in glass. These adhesive forces are stronger than water's cohesive forces, its hydrogen bonds. So the water gets pulled up the sides of the tube, forming that curved concave meniscus.
And mercury. It curves the other way, convex.
Because mercury's cohesive forces, the metallic bonds between mercury atoms, are much stronger than its adhesive forces to glass. So it pulls itself inward, minimizing contact with the glass.
Fascinating. And what about how easily a liquid flows, like honey versus water?
That's viscosity. It's simply a measure of a liquid's resistance to flow.
So honey is very viscous.
Extremely. And viscosity is directly related to intermolecular forces. Stronger forces mean higher viscosity. Glycerol, for instance, is thick and syrupy because it has multiple sites for hydrogen bonding.
Does molecule shape matter too?
Absolutely. Long, tangly molecules like the complex hydrocarbons in motor oil or grease tend to get physically caught up with each other, increasing viscosity compared to shorter, more compact molecules like those in gasoline. Think pangled spaghetti versus marbles.
That makes perfect sense. You mentioned smart fluids earlier.
Right.
How do they tie into viscosity?
Right, those magnetorrheological fluids, or MR fluids, they're a brilliant application. Usually they're an oil with tiny iron particles suspended in it. Normally it flows like a regular oil, but apply a magnetic field.
The iron particles line up?
Instantly, they form chains along the magnetic field lines, making the fluid incredibly viscous, almost solid-like, in milliseconds.
Wow. So you can control the stiffness of a car's suspension on the fly.
Exactly. Or dampen vibrations in buildings during an earthquake. Turn off the magnet, and it flows freely again. It's controlling those intermolecular, interparticle interactions externally.
Incredible stuff. Okay, let's shift from the flowing world of liquids to the more structured world of solids. Feels like a different ballgame.
It is, in many ways, though still governed by those fundamental forces. Broadly, we divide solids into two types.
Okay.
Crystalline solids, which have a highly ordered, repeating internal structure. Think salt, sugar, metals, diamonds. They often have flat faces and sharp angles reflecting that internal order.
Like tiny building blocks repeating over and over.
Precisely. And the other type is amorphous solids. Amorphous means without form. These lack that long-range order. Glass is the classic example. Rubber, some plastics too, their internal structure is more jumbled, like a frozen liquid.
So for the crystalline ones, how do we describe that repeating pattern?
We use the concept of a lattice, which is just a 3D grid of points representing the positions of the components, atoms, ions, or molecules. And the smallest repeating unit of this lattice is called the unit cell. Stack these unit cells in all 3 dimensions, and you build the entire crystal.
But how do we know what that structure is? We can't just, look at it.
We can't see atoms directly with light, no.
Yeah.
But we can use X-ray analysis, specifically X-ray diffraction.
How does that work?
Well, X-rays have wavelengths that are similar in size to the distances between atoms in a crystal. When you shine a beam of X-rays onto a crystal, the waves scatter off the regularly arranged atoms. Because the atoms are in this regular pattern, the scattered waves interfere with each other. They can either reinforce each other, constructive interference, or cancel each other out, destructive interference, depending on the angles and distances.
So you get a pattern.
Exactly. A unique diffraction pattern of bright spots on a detector. By analyzing the angles and intensities of these spots, scientists can work backward using equations like the Bragg equation to figure out the precise arrangement of atoms, the distances and angles within the unit cell.
Wow. So that's how they determine the structure of, complex proteins, too.
Yes, it's an incredibly powerful technique, fundamental to chemistry, materials science, and biology.
Okay, so we know how we find the structure. You mentioned crystalline solids have repeating units. What kinds of things make up those units? Does it change the solid's properties?
Oh, absolutely. It makes a huge difference.
Yeah.
We classify crystalline solids based on what's at those lattice points and the forces holding them together.
Okay, what are the main types?
First, ionic solids. Here, the lattice points are occupied by positive and negative ions, like sodium chloride, NaCl.
Held together by electrostatic attraction.
Right, strong ionic bonds. This makes them typically hard, brittle, and have very high melting points. They don't conduct electricity as solids, but they do when melted or dissolved in water because the ions become free to move.
Okay, ionic. What's next?
Molecular solids. In these, the lattice points are occupied by whole, discrete molecules, like water molecules in ice, or CO2 molecules in dry ice, or sugar molecules.
And what holds them together?
The weaker intermolecular forces we talked about earlier. Dipole forces, hydrogen bonds, London dispersion forces.
Ah, so because the forces are weaker, they probably have lower melting points.
Generally, yes. Much lower than ionic solids. They tend to be softer and are usually poor electrical conductors because the electrons are localized within the covalent bonds of each molecule.
Makes sense. Any others?
Yes, the third main category is atomic solids, where individual atoms sit at the lattice points. But this category is quite diverse, so we subdivide it further based on bonding.
Okay.
You can have metallic solids like copper or iron. Here, metal atoms are held together by metallic bonding, that sea of electrons idea.
Right, which makes them conductive and malleable.
Exactly. Then you have network solids, sometimes called covalent network solids. Think of diamond or quartz, silicon dioxide. Here, atoms are connected by a vast network of strong directional covalent bonds, It's like one giant molecule.
So they'd be very hard and have high melting points.
Extremely hard, yes, and typically very high melting points because you have to break strong covalent bonds to melt them. Diamond is the classic example.
And the last type of atomic solid.
That would be the group 8A solids, the noble gases, when they freeze at very low temperatures. Here is just individual atoms held together by only London dispersion forces.
So they'd have really low melting points.
Extremely low. Argon melts at negative 189 degrees C. So you see, just knowing it's an atomic solid isn't enough. Is it metallic, network, or group 8A? The bonding dictates properties like melting point, hardness, conductivity, everything.
That's a great overview. Let's maybe zoom in on metals a bit more. You mentioned conductivity, malleability. That electron C model seems key.
It's a good starting point, the electron C model. Picture a regular grid of positive metal ions, and the valence electrons are just delocalized. They form a mobile C or glue that flows around the cations, holding everything together.
And that explains conductivity, electrons moving freely.
Yes, and malleability too. If you hit a metal, the layers of ions can slide past each other without breaking the metallic bond because the electron C just flows around and adjusts, unlike an ionic crystal, which shatters.
Is there a more advanced model?
Yes, the band model, which comes from molecular orbital theory. It thinks about the atomic orbitals of all the metal atoms merging to form a vast number of molecular orbitals that are incredibly close in energy. They form continuous bands.
Bands of energy levels.
Sort of, yeah. You get filled bands, valence bands, and empty or partially filled bands, conduction bands. In metals, the conduction band is either partially filled or overlaps with the valence band, meaning electrons can easily jump into empty energy states and move freely throughout the metal when you apply an electric field. That's efficient conductivity.
Okay. And metals often aren't pure, right? We use alloys.
Very true. Alloys are mixtures containing metals designed to have specific, improved properties. There are two main types.
Future.
Substitutional alloys, where some atoms of the host metal are replaced by atoms of another metal of similar size. Brass, for example, is copper with some zinc atoms substituted in.
Okay, swapping atoms.
And interstitial alloys, where much smaller atoms fit into the holes or interstices between the host metal atoms. Steel is the classic example. Small carbon atoms fit into the gaps in the iron lattice.
And that makes it harder.
Much harder and stronger than pure iron. Those small interstitial atoms disrupt the regular layers, making it harder for them to slide past each other. But it often makes the metal less ductile, too. Different types of steel just vary the amount of carbon and sometimes add other elements.
Fascinating how just adding a tiny bit of something else changes it so much. Now, what about those network solids, like carbon? Diamond and graphite seem like total opposites, but they're both pure carbon.
It's one of the best examples of how structure dictates properties. In diamond, every carbon atom is bonded tetrahedrally to 4 other carbon atoms using sp3 hybrid orbitals, strong, single, covalent bonds throughout.
Creating that rigid 3D network.
Exactly. It's incredibly hard. And the energy gap between its filled valence band and empty conduction band is huge, so electrons can't easily jump across. That makes diamond an excellent electrical insulator.
Okay, graphite.
Graphite's totally different. Carbon atoms are arranged in flat layers. Within each layer, atoms are bonded in fused 6-membered rings using sep2 hybridization.
Like chicken wire sheets.
Kind of, yeah. And importantly, there are delocalized pi electrons within each layer, just like in benzene. These mobile electrons make graphite a good electrical conductor, but only along the layers.
And what holds the layers together?
Very weak London dispersion forces, so the layers can slide past each other very easily.
Ah, that's why it's slippery. Used as a lubricant.
Exactly. Same element, carbon, but arranging the atoms differently gives you the hardest known natural substance and a soft lubricant. Bonding and structure are everything. And of course, there's graphene, just a single one of those graphite layers. Incredibly strong, amazing conductor. Lots of research there.
Wild. What about silicon? It's right below carbon.
Silicon is the basis for so much modern technology. Like carbon, it forms a diamond-like network structure. But crucially, the energy gap in its band structure is smaller than diamonds.
So it's not quite an insulator.
Right. At room temperature, a few electrons have enough energy to jump the gap into the conduction band. This makes pure silicon an intrinsic semiconductor. Its conductivity is low, but it's there, and it increases with temperature, unlike a metal.
But we need better conductivity for electronics.
Yes, and that's achieved through doping, intentionally adding tiny, controlled amounts of impurities.
How does that work?
2 ways. Add an element with more valence electrons than silicon, like arsenic, which has 5.
Right.
Arsenic replaces the silicon atom, which has 4, so there's one extra electron that isn't needed for bonding. This extra electron easily moves into the conduction band that's called an N-type semiconductor for negative charge carriers,
Yeah.
electrons.
Extra electrons. What's the other way?
Add an element with fewer valence electrons, like boron, which has 3. When boron replaces silicon, there's a missing electron needed to form the 4 bonds. This creates an electron vacancy, or a hole.
A hole?
Yeah, think of it as a spot where an electron could be. An electron from a nearby bond can jump into this hole, leaving a new hole behind. So the hole effectively moves. Since it represents the absence of a negative electron, it acts like a positive charge carrier. This is a p-type semiconductor for positive charge carriers. Holes.
Clever. So you can make silicon conduct using either extra electrons or these holes.
Precisely. And the real magic happens when you join a piece of N-type silicon to a piece of p-type silicon. You create a p-n junction.
And what does that do?
It acts as a rectifier. It allows electric current to flow easily in one direction, from P to N, but strongly resists flow in the opposite direction. This ability to control current flow is the absolute foundation of diodes, transistors, integrated circuits, basically all modern electronics.
Mind-blowing that just adding tiny impurities can do all that. Okay, we've covered the structures. What about change in between states? Melting, boiling, dynamic
Advanced changes. Let's take vaporization liquid to gas. It's always endothermic. You have to put energy in to overcome those intermolecular attractions.
Like boiling water.
Exactly. And water's heat of vaporization, HVAP, is very high, remember, almost 41 kJ/mol because of hydrogen bonding. That's why sweating cools you down. The evaporating water takes a lot of heat from your skin, and why coastal areas have moderate climates.
Okay. What about vapor pressure?
If you put a liquid in a closed container, molecules start evaporating into the space above it. But some gas molecules will also hit the surface and condense back into liquid.
So it's a two-way street.
Yes.
Yeah.
Eventually, the rate of evaporation equals the rate of condensation. You reach a dynamic equilibrium. The pressure exerted by the gas molecules at this equilibrium is the vapor pressure of the liquid at that temperature.
Does it depend on the liquid?
Absolutely. Liquids with strong intermolecular forces have low vapor pressures. Fewer molecules have enough energy to escape. Liquids with weak forces, like ether, are volatile and have high vapor pressures.
And temperature.
Big effect. Higher temperature means more molecules have enough kinetic energy to escape the liquid, so vapor pressure increases dramatically with temperature. Got it. What about solid to gas directly?
That's sublimation. Dry ice, solid CO2, does this at room pressure. Iodine crystals, too. Just skips the liquid phase entirely.
If we track temperature as we add heat, what does that look like?
That gives you a heating curve. You start with the solid, add heat, and its temperature rises. Then, when you hit the melting point...
So it stays flat for a while.
Exactly. The temperature holds constant even though you're still adding heat. All that energy is going into breaking the forces, holding the solid together, converting it to liquid. That energy is the heat of fusion.
COFUS.
Then the liquid heats up.
Until it reaches the boiling point. And again, you get another plateau. Temperature stays constant while the liquid turns into gas. All the added energy goes into overcoming the intermolecular forces in the liquid at the heat of vaporization.
COFEF. And UF-step is usually bigger than OFSS.
For most substances, yes. Especially water. It takes much more energy to completely separate the molecules into a gas than just to loosen them up into a liquid. Once all the liquid is gas, then the gas temperature starts to rise again.
Sometimes weird things happen though, right? Like water getting colder than freezing without turning to ice.
Yes, supercooling. Liquids can sometimes be cooled below their freezing point without solidifying, especially if they're very pure and undisturbed. They need a nucleation site, like a dust particle or a rough spot, to start crystal formation. Similarly, liquids can be superheated above their boiling point without actually boiling, which can be dangerous because it might suddenly boil violently. That's called bumping. Boiling chips in labs prevent this.
Right, gives it a place to start boiling smoothly. Okay, so temperature and pressure clearly control the state. Is there a map for this?
There is. It's called a phase diagram. It's a graph that shows the stable phase, solid, liquid, or gas, of a substance at any given combination of temperature and pressure, assuming a closed system.
Let's look at water's diagram. You said it's unusual.
It is. The most striking feature is the boundary line between solid, ice, and liquid. It slopes backwards to the left, negative slope.
What does that mean?
It means that as you increase the pressure on ice, its melting point actually decreases. For almost everything else, increasing pressure favors the denser phase, which is usually the solid, so the melting point increases.
But ice is less dense than water.
Exactly. That's the key. Increasing pressure on ice makes it want to become the denser liquid phase, so it melts at a lower temperature under pressure.
And that explains ice skating. The blade pressure melts the ice.
That's the classic explanation, yes. It also explains why pipes burst when water freezes, ice expands, and crucially, why ice floats, insulating lakes and allowing aquatic life to survive winter. It's a really unique and vital property.
What else does the diagram show?
It shows the triple point. That's a specific temperature and pressure where solid, liquid, and gas can all coexist in stable equilibrium. For water, it's 0.01 degrees C and about 4.6 torr, a very low pressure.
All three phases at once? Weird.
It is. And then at high temperatures and pressures, you reach the critical point. Beyond this point, the distinction between liquid and gas disappears. You just have a supercritical fluid, which has properties of both.
And boiling point changes with pressure too, right? Like on a mountain.
Yes, the diagram shows that. The boiling point is where the liquid's vapor pressure equals the external pressure. At higher altitudes, atmospheric pressure is lower, so water boils at a lower temperature. It takes longer to cook things.
Okay, what about CO2? Its diagram must look different if dry ice sublimes.
It does. Its solid-liquid line slopes forward, positive slope, because solid CO2 is denser than liquid CO2, which is normal. But the key difference is where 1 atmosphere pressure lies. At 1 atm, the temperature line crosses directly from the solid region to the gas region as you warm it up. The triple point is actually above 1 atm pressure.
So you only get liquid CO2 at higher pressures.
Exactly. At standard pressure, solid CO2 just turns straight into gas sublimation, perfect for keeping things cold without making them wet. And in a fire extinguisher, liquid CO2 is kept under high pressure. When released, it expands rapidly and cools, turning into gas and solid snow, smothering the fire.
Phase diagrams really tie it all together. So recapping for everyone listening, what are the big takeaways?
I think the biggest one is just how crucial those seemingly subtle intermolecular forces are. They dictate whether something is a solid, liquid, or gas, and they control key properties like boiling points, viscosity, and surface tension.
And we saw how macroscopic properties we observe every day link directly back to what's happening between individual molecules.
Absolutely. We also saw the amazing diversity of solids, the way metals use that electron sea, the incredible strength of network solids like diamond, and the clever engineering behind semiconductors that allows for all our modern tech.
Yeah, the doping and PN junctions are just genius.
And finally, understanding phase changes and phase diagrams lets us predict and explain how substances transform under different conditions, why ice floats, why dry ice sublimes, how pressure affects boiling.
So knowing this stuff really does help explain the world around us, from everyday things like cooking or condensation to high-tech materials. It's fundamental.
It really is. It connects the microscopic world of atoms and molecules to the macroscopic world we experience.
Okay, here's a final thought to leave you with. Next time you pour yourself a glass of water or see frost on a window, take a second to picture those H2O molecules. Think about the constant dance of hydrogen bonds forming and breaking, the balance between kinetic energy pushing them apart and those forces pulling them together. What other everyday things can you now look at and see the hidden chemistry of intermolecular forces at play? Thank you so much for joining us on this deep dive into the states of matter. We hope you feel a bit more clued in and maybe even more curious than before from the Deep Dive team. Thanks for listening.